Hello everyone, welcome to my presentation for PHN 313 Signals and Systems. I'll be presenting on the topic adaptive filtering for signal processing. To begin our discussion, we'll be looking at some very basic background behind filters and noise. Beginning with what is a filter? Well, a filter is a device which may be analog or digital which is used to suppress unwanted or useless components from a signal. Such components are called noise. A filter can also be an algorithm or a mathematical model. This line is highlighted because our discussion will primarily be about using algorithms as filters. Now, where does this noise come from? In realistic systems, there is always some noise, which may be due to fluctuations in the ambient conditions, limits in the resolution of a sensor, electrical interference, imperfections in the transmission medium, etc. All this means is that we cannot have a perfect information about the state of a system, only an estimation. Okay, now we'll talk about the functions of a filter. Despite what the name suggests, a filter does not just do filtering. A filter can be used to perform three basic tasks in information and signal processing. Filtering, which is extracting useful information from a signal at a time t using data available before and at time t, which is what is most commonly associated with a filter. Smoothing, extracting useful information about a signal at a time t prime using data collected before and after t prime. And prediction, extracting information about a signal at a time t plus tau using data available before and at time t. While both filtering and predictions are real-time operations, smoothing is not. Real-time operations make use of data available at present and from the past. That is, they are causal. In essence, a filter can only provide an estimation of a true signal. Thus, filters are also called estimators. More accurately, we should say that a filter is a type of estimator. In statistics, an estimator is a tool that approximates unknown parameters based on all the measured data available. It is a function that associates a parameter estimate to each possible sample that we can observe. Now that we have an understanding about the functions of a filter, let us try to view these operations as statistical problems, constraining ourselves to linear filtering problems for simplicity. When we are designing a filter, we assume we have some data available about the statistics of the signal and the noise. With this assumption, the simplest and the most useful approach to filtering is minimum square error method. For problems where the signal or the noise is stationary, a Wiener filter is used. For non-stationary problems, a Kalman filter is used. A stationary signal is just a signal whose statistical characteristics don't change with time. In reality, very few signals may be considered stationary, with most being subject to some sort of time varying or space varying noise. Therefore, it is the non-stationary problem that is our main concern here. I'll be spending some time on the Wiener filter in the next slide, but I'll just quickly mention that the Kalman filter is itself a type of adaptive filter that operates on state space models. The Wiener filter is one of the earliest techniques designed to reduce additive random noise in images and signals. A key application of the Wiener filter is deconvolution, a process that helps reverse the effects of convolution on recorded data, which is especially useful in image restoration or audio processing. The Wiener filter operates in the domain of stationary signals and assumes a priori knowledge of the signal and noise statistics. It can be understood as a linear time invariant system, making it a causal filter. The Wiener filter can also be made adaptive by continuously adjusting the convolution process based on signal information. While the Wiener filter on its own is not an adaptive filter, the reason I mention it now is that we'll be using an adaptive version of the Wiener filter which is included in MATLAB. So what is the need for adaptive filters? When we are designing a filter such as a Wiener filter, we require a priori information about the statistics of the data to be processed. If this data is not available with us, the Wiener filter either cannot be designed or will no longer be optimum. So possible workaround that we might think of is just using an estimate and plug method. A filter that estimates the signal statistics and then plugs the results into a non-recursive formula to obtain the filter parameters. But for real-time signal processing, computational load for this kind of procedure can be excessive. Thus, we introduce adaptive filters to overcome this problem. Now, I'll try to explain what an adaptive filter is as simply as possible. When we have incomplete knowledge about signal statistics, using an initial guess and a recursive algorithm, we can come up with an adaptive filter. An adaptive filter will then converge to the optimum conditions that are determined by the Wiener filter, given that the signal was stationary. If the signal is non-stationary, as is the case in most signals, this will allow us to track the changes in statistics of the input data, provided that the variations are small. Adaptive filters are self-adjusting and change their filtering parameters based on the input characteristics in real time, which is what makes them adaptive. This allows them to track changes in the signal environment, making them effective for applications where the signal or the noise is non-stationary, that is, time varying. Some commonly used adaptive algorithms include the least mean squares and the recursive least squares algorithm. Later on, we'll be focusing primarily on the least mean squares algorithm. So, what is the role of adaptive filters in signal processing? Adaptive filters have a very important role in modern signal processing. They are used for echo cancellation in communication devices, noise reduction and channel equalization in audio devices, signal enhancements in biomedical systems, and adaptive control systems. They have many more applications. Adaptive filters work generally for adaptation of signal changing environments, spectral overlap between noise and signal, unknown or time varying noise. What advantages do adaptive filters offer over traditional filters? Well, adaptive filters play a crucial role in both causal and non-causal systems. In real-time applications, they function as causal systems, and in tasks like smoothing, they operate as non-causal systems, providing flexibility in signal processing. Some advantages over traditional filtering methods include adaptive filters just adjust their coefficients continuously based on the input signal, making them ideal for handling time-varying signals, unlike most fixed convolution filters. They perform well in environments where signal and noise statistics change over time, whereas Fourier-based methods assume stationary signals, limiting their effectiveness in dynamic scenarios. Traditional methods like Wiener and Fourier filters require prior knowledge of the signal/noise characteristics, but adaptive filters learn these in real time, which makes them better for unpredictable environments. Also, traditional filters, which are based on convolution and Fourier methods, aren't particularly good when it comes to dealing with non-integrable functions. However, adaptive filters have no such problem. While adaptive filters do offer some benefits over traditional filtering methods, they do have their own problems. Firstly, an algorithm such as the LMS algorithm can have a slow convergence rate. In practical terms, it means that it can take a long time for the filter to learn the optimal filter coefficients. Another is that certain adaptive filter algorithms such as the RLS or more sophisticated methods like the Kalman filters can be computationally expensive, as they involve matrix operations and recursive calculations, which means they demand more memory and more processing power. These algorithms are also typically very sensitive to the initialization conditions. A poor first step may mean that an algorithm may not converge at all. There is also some inherent processing delay because these algorithms change their coefficients on a sample by sample basis. Finally, many adaptive filters such as the LMS and RLS are designed based on the assumption that the relationship between the desired signal and the input signal is linear. However, many real-world systems are non-linear and linear adaptive filters may not perform well in these scenarios. The simplest implementation of an adaptive filter is the least mean square algorithm for the finite impulse response filter. Let's consider this noise cancellation system using an adaptive filter model. Within this diagram, SN stands for desired speech, NN stands for the corrupting noise, DN stands for distorted signal, XN stands for the noise signal, and YN stands for the noise estimate. The noise signal X of n is correlated to the corrupting noise N of n, originating from the same source. X of n and N of n are not correlated to the desired signal S of n. When two signals are uncorrelated, it means there is no direct relationship between them. What this means for us and why this is important is that since the desired signal S of n is uncorrelated to both the noise signals, this ensures that the adaptive filter won't mistakenly cancel out part of the desired signal while removing the noise. We assume the first channel noise N of n to be a linear filtered version of the second channel noise X of n. Noise source is time varying so that we can estimate the corrupting noise N of n using an adaptive filter. The adaptive filter contains a digital filter with adjustable coefficients and the LMS algorithm to modify the values of the coefficients for filtering each sample. The adaptive filter then produces an estimate of the noise Y of n, which will be subtracted from the corrupted signal d of n, which is the sum of s of n and n of n. When the noise estimate equals or approximates the noise n of n in the corrupted signals, that is, y of n is approximately equal to n of n, the error signal e of n, which is equal to d of n minus y of n, will approximately equal s of n, which will approximate the clean speech signal s of n. Hence, we have cancelled the noise. The FIR filter that I'm about to show you is one tap to simplify the algebra. What one tap means is that the weights used for the estimate noise signal is a scalar instead of a vector or a matrix that would be used for a more realistic and complicated system. The filter adjustable coefficient Wn is adjusted based on the LMS algorithm. Wn plus 1 is equal to Wn plus 0.01 times En times Xn. Wn is the current weight, Wn plus 1 is the next weight based on the LMS. The value of 0.01, which is the learning rate, here is chosen arbitrarily and controls the speed of the coefficient change. Y of n is equal to Wn times x of n, while En is equal to d of n minus y of n. So, with the LMS adaptive filter, and with the help of the table given here, which contains the values for all the signals at different sample points, we were able to obtain the original signal from the distorted signal. The adaptive filter revealed to us that the original signal was just a sinusoidal wave. Finally, we are in the position to start implementing our own adaptive filter. I have written this code in MATLAB. What it does is that it takes an input from the user for an audio file. After we insert the audio file, that audio file, if it is in stereo sound, is converted into mono. We do that because we need the audio signal to be single channel. After that is done, we start sampling the audio. After sampling is done, we can artificially add noise into the audio. And after that, we initialize the learning rate, the adaptive filter coefficients, the filter output, and the error signal. After all of that, the LMS algorithm gets to work. When the LMS algorithm is done filtering the signal, what we have is the original signal, the corrupted signal, the noise signal, and the filtered audio that is being plotted. We use these plots to compare the signals in time domain. After that, we can use Fourier transform to convert the signals into frequency domain so that we can also compare the frequency spectra. From the output, we can tell that our algorithm has essentially performed the work of a low-pass filter by removing the high-frequency signal noise. This filtering was done despite us having no idea at the beginning that a low-pass filter would be needed to filter the noise. This also helps solve one of the most common problems that comes up when trying to design a low-pass filter electrically. When we're trying to design a low-pass filter electrically, we have to consider what values of R and C we are going to use such that we can filter out the specific frequencies that we do not want in our signal. This is something that we did not have to do while using an adaptive filter algorithm. MATLAB's implementation of the adaptive Wiener filter can be used to filter noisy images. I've written some basic code to do exactly that. I've given MATLAB an image of my own choosing. That image is then converted into grayscale. After being converted into grayscale, has some Gaussian noise applied to it. And after that, it undergoes Wiener filtration to obtain a noiseless image. Then I just print the original image, the image with the added Gaussian noise, and the image with the noise removed by the Wiener filter. While it may not be immediately obvious for those watching this presentation, there is a huge difference between the image with the added Gaussian noise and the image where the Gaussian noise has been removed to some extent by the Wiener filter. The image with the noise removed appears much smoother and is easier on the eyes compared to the image with the Gaussian noise. Adaptive filtering techniques are not new, and the field continues to evolve with new techniques, particularly involving machine learning, deep learning, and advanced algorithms. To wrap up this presentation, I'll just mention a few emerging methods in adaptive filtering: neural network based adaptive filtering, deep learning for adaptive filtering, machine learning based adaptive filtering, wavelet based adaptive filtering, and sparse adaptive filtering. Here are the references for all the information used in this presentation. I hope you enjoyed my presentation and thank you for your time.